Hi friends, welcome back to MOOC course on differential calculus. In the coming sessions, we focus on curve tracing. Keeping this in mind, let us familiar with some terminologies that will help us in sketching curves. We are living in a highly competitive world, and in every business, people are trying to maximize their profit or to minimize expenditure. In this session, we describe how to find maximum and minimum of mathematical functions. Intuitively, a function f has a maximum at some point, say x equal to c, if the value f of c dominates all other values of f. Mathematically, a function f defined on a domain D has a maximum or absolute maximum at x equal to c if f of c is greater than or equal to f of x for all x in the domain D. Then f of c is called the maximum value of f in the domain D. Similarly, f has a minimum or absolute minimum at x equal to c if f of c is less than or equal to f of x for all x in the domain D. Then f of c is called the minimum value of f in the domain D. The point c is called a point of extremum, that is maximum or minimum. For example, consider the function f of x equal to x square, whose graph is the curve y equal to x square that represents the parabola shown in figure. From the figure, it is obvious that the function has minimum value 0 and it occurs when x value is 0. Mathematically, f of 0 equal to 0 less than or equal to x square equal to f of x for every x in the interval minus infinity to plus infinity. Thus, f has a minimum at x equal to 0. However, by looking at the graph, we conjecture that f never attains a maximum on the interval minus infinity to plus infinity. We verify this mathematically. If there is a c in the interval minus infinity to plus infinity, such that f of c is greater than or equal to f of x for all x in minus infinity to plus infinity, then by the definition of f, c square is greater than or equal to x square for all x in the interval minus infinity to plus infinity, which is obviously not true, because for instance, c square is greater than or equal to c plus 1 whole square is false. This proves that f never attains a maximum on the domain minus infinity to plus infinity. This example shows that a given function may not have a point of maximum on the given domain. But if the domain is restricted to 0 to 3, by looking at the graph of f, we infer that f attains its maximum value 9 when x value is 3. This is true since f of 3 equal to 3 square equal to 9 is greater than or equal to x square equal to f of x for all x in the closed interval 0 to 3. Hence, the point 3 is a point of maximum on the domain 0 to 3. But if the domain is restricted to the closed interval minus 3 to plus 3, by looking at the graph of f, we infer that f attains its maximum value 9 when x value is 3 or minus 3. That is, f of 3 equal to 3 square equal to 9 is greater than or equal to x square equal to f of x for all x in the closed interval minus 3 to plus 3, and f of minus 3 is equal to minus 3 whole square equal to 9 is greater than or equal to x square equal to f of x for all x in the closed interval minus 3 to plus 3. Hence, the points of maximum of the function over the closed interval minus 3 to plus 3 are 3 and minus 3. This example shows that a function may have more than one maximum over an interval. If we take a look at the graph representing the petrol price in India for a period of 10 years starting from the year 2004, we observe that the absolute maximum is 73.70 and is attained in the year 2014. However, if we restrict ourselves to 5 years from 2005 to 2009, then the maximum value is 48.65 and it is attained in the year 2008. Such values behaving like maximum values in small intervals are called local maximum. Analogously, we can define local minimum. In fact, 43.37 attained in the year 2009 is a local minimum. We say that a function has a local maximum value at an interior point C of its domain if f of c is greater than or equal to f of x for all x in some open interval containing c. A function f has a local minimum value at an interior point C of its domain if f of x is greater than or equal to f of c for all x in some open interval containing c. By looking at the graph of f of x equal to x cube minus 3x, we can see a local maximum at x equal to minus 1 and a local minimum at x equal to 1. We verify this theoretically as follows. F of minus 1 equal to 2 is greater than or equal to f of x for all x in the interval minus 2 to 0, an open interval containing minus 1. So that f has a local maximum at x equal to minus 1. Similarly, f of 1 equal to minus 2 is less than or equal to f of x for all x in 0 to an open interval containing 1. So that f has a local minimum at x equal to 1. However, we observe either from the graph or from the fact that f of minus 1 equal to 2 less than 18 equal to f of 3, so that x equal to minus 1 is not a point of absolute maximum on the interval minus 4 to 4, but a point of absolute maximum on 0 to 2. This shows a point of absolute maximum on a smaller interval need not be a point of absolute maximum on larger intervals. Similarly, x equal to 1 is not an absolute minimum on bigger intervals. This function is an example where there are local maximum and local minimum, but neither absolute maximum nor absolute minimum on the entire domain. An endpoint C is said to be a local maximum if f of c is greater than or equal to f of x holds in a semi-open interval containing c, where f is defined. An endpoint C is said to be a local minimum if f of c is less than or equal to f of x holds in a semi-open interval containing c, where f is defined. In the figure, the function defined on the closed interval a b has a local minima at a, e and b and local maxima at c and d. A is an absolute minimum point and d is an absolute maximum point. By the definition, it is clear that every absolute maximum is a local maximum and every absolute minimum is a local minimum. However, the converse is not true, as in the figure above. The local maximum c is not an absolute maximum and the local minima e and b are not absolute minima. The following theorem, known as first derivative theorem, is useful in determining local extrema. First derivative theorem says that if f has a local maximum or minimum value at an interior point c and if f is differentiable at c, then f dash of c equal to 0. Proof: since f is differentiable at c, then by the definition of derivative, f dash of c is equal to limit x going to c f of x minus f of c upon x minus c. We know that a function g of x approaches the two-sided limit L as x approaches c if and only if g of x approaches the same value L as x approaches c from the left as well as from the right. Hence, f dash of c is equal to limit x going to c f of x minus f of c upon x minus c is equal to limit x going to c plus f of x minus f of c upon x minus c is equal to limit x going to c minus f of x minus f of c upon x minus c. Suppose f has a local maximum at x equal to c. Then f of c is greater than or equal to f of x for all x sufficiently near to c. That is, f of c minus f of x is greater than or equal to 0 for all x sufficiently near to c. In particular, f of c minus f of x is greater than or equal to 0 for all x less than c and x sufficiently near to c. that is f of c minus f of x is greater than or equal to 0 for all x minus c less than 0 and x sufficiently near to c. Hence, f of c minus f of x upon x minus c is less than or equal to 0 for all x minus c less than 0 and x sufficiently near to c. That is, for x less than c and x sufficiently near to c, we have f of x minus f of c upon x minus c is greater than or equal to 0. So that limit x going to c minus f of x minus f of c upon x minus c is greater than or equal to 0. Hence, f dash of c is equal to limit x going to c minus f of x minus f of c upon x minus c is greater than or equal to 0. Equation 1. Similarly, for x greater than c and x sufficiently near to c, we get f of x minus f of c upon x minus c is less than or equal to 0. So that f dash of c equal to limit x going to c plus f of x minus f of c upon x minus c is less than or equal to 0. Equation 2. From 1 and 2, it follows that f dash of c is equal to 0. We have an analogous proof if f has a local minimum at x equal to c. This completes the proof. This theorem can be restated as a function f has a local extremum at an interior point x equal to c, then either f is not differentiable at c or f dash of c is equal to 0. A point x equal to c is called a critical point if either f is not differentiable at c or f dash of c equal to 0. We started our discussion with the aim of determining absolute maximum and minimum. There are two questions to be answered. 1. Whether the maximum and minimum exist. 2. Determine them when they exist. The following theorem says that the first question has an affirmative answer for continuous functions defined on closed bounded intervals. Theorem: any continuous function on a closed bounded interval a b attains its maximum and minimum. That is, there are c1 and c2 in the interval a b such that f of c1 is less than or equal to f of x less than or equal to f of c2 for all x in the closed interval a b. This theorem, when combined with the first derivative theorem, gives us the following result. Theorem: if a function f defined on a closed interval a b is differentiable on the open interval a b and continuous at the end points, then f attains maximum at some point c in the closed interval a b, and either c is an end point or f dash of c is equal to 0 or f is not differentiable at c. We now discuss the procedure for finding the absolute extrema of continuous functions on the closed interval a b. Supported by the above theorem, for finding the absolute extrema of continuous functions on the closed interval a b, we proceed as follows. Step 1. Determine the critical points of f in the open interval a b. Step 2. Evaluate f at all critical numbers and at the end points a and b. Step 3. The largest of the values in step 2 is the absolute maximum value of f on the closed interval a b, and the smallest value is the absolute minimum. As an example, consider f of x equal to 2x cube minus 9x square plus 1 on the closed interval minus 1 comma 2. Step 1. Being a polynomial, this function is differentiable everywhere and the derivative is given by f dash of x equal to 6x square minus 18x. Hence, to find critical points, we equate f dash of c equal to 0, giving 6c square minus 18c equal to 0. This gives 6c into c minus 3 equal to 0, which gives c is equal to 0 and c equal to 3. Thus, critical points are c equal to 0 and c equal to 3. Step 2. At critical points, local extrema are f of 0 equal to 1 and f of 3 equal to minus 26. At boundary points, f of minus 1 is equal to minus 10 and f of 4 is equal to minus 15. Step 3. Hence, maximum among all these values is 1 and minimum is minus 26. Hence, f has an absolute maximum at x equal to 0 and absolute minimum at x equal to 3. Warning: it should be remembered that for a differentiable function f condition on derivative, that is f dash of c is equal to 0, is only a necessary one and is not sufficient to say that x equal to c is a local extrema. For example, the function f of x equal to x cube is differentiable. In fact, f dash of x equal to 3x square and hence f dash of 0 equal to 0. However, x equal to 0 is neither a local maxima nor a local minima as seen from the graph of f of x equal to x cube. First derivative theorem helps us to identify extrema, but it does not distinguish maxima and minima. For example, a is a local minimum and b is a local maximum for the function represented by the given graph. Here the function value at local minimum is greater than the function value at local maximum. Thus, just by looking at the function values corresponding to the extremum points, we may not be able to say whether it is a local maximum or minimum. Hence, we need some other tool by which we can separate local maxima and local minima. The second derivative helps us in doing this. Let f be a function that has a local maximum at x equal to c, and let f be twice differentiable at x equal to c. Then first derivative f dash x is near x equal to c, and as seen from the figure, the slope of tangents, that is f dash of x, keep on decreasing near c, so that f dash of c is less than or equal to f dash of x for all x less than c where x is sufficiently close to c. That is, f dash of x minus f dash of c is greater than or equal to 0 for all x minus c less than 0 where x is sufficiently close to c. Then f dash of x minus f dash of c upon x minus c is less than or equal to 0 where x is sufficiently close to c. This would imply that left hand derivative of f at c is less than or equal to 0. That is, limit x going to c minus f dash of x minus f dash of c upon x minus c is less than or equal to 0. Since f double dash of c exists, the value f double dash of c is the same as the left hand and right hand derivatives of f dash at c. Hence, in particular, we obtain f double dash of c equal to limit x going to c minus f dash of x minus f dash of c upon x minus c less than or equal to 0. Similarly, if f has a local minimum at x equal to d, then f is twice differentiable at x equal to d, then first derivative x is near x equal to d, and as seen from the figure, the slope of the tangents, that is f dash of x, keep on increasing near d, so that f dash of x is less than or equal to f dash of d for all x greater than d, x sufficiently close to d. This would imply f double dash of d equal to limit x going to d plus f dash of x minus f dash of d by x minus d is greater than or equal to 0. The procedure for finding local maxima and minima is summarized as: step 1, equate f dash to 0 to get a local extrema. Step 2, evaluate f double dash at local extrema. If f double dash of c is less than 0, then x equal to c is a local maximum, and if f double dash of c is greater than 0, then x equal to c is a local minimum. If f double dash of c equal to 0, then the second derivative test fails. For example, consider f of x equal to 5x cube plus 2x square minus 3x. This function is differentiable everywhere, and f dash of x is equal to 15x square plus 4x minus 3. Now, f dash of x is equal to 0 implies 15x square plus 4x minus 3 is equal to 0, which is a quadratic equation whose roots are x equal to minus 4 plus or minus square root of 4 square minus 4 into 15 into minus 3 whole divided by 2 into 15, which is equal to minus 4 plus or minus square root of 16 plus 180 whole divided by 30, which is equal to minus 4 plus or minus 14 divided by 30, which is equal to minus 3 by 5 or 1 by 3. Thus, we get two extrema minus 3 by 5 and 1 by 3. Now, we apply second derivative test to classify them local maxima or minima. We have f double dash of x equal to 30x plus 4. Thus, f double dash of minus 3 by 5 equal to 30 into minus 3 by 5 plus 4, which is equal to minus 18 plus 4, which is equal to minus 14, which is less than 0. And f double dash of 1 by 3 is equal to 30 into 1 by 3 plus 4, which is equal to 10 plus 4, which is equal to 14, which is greater than 0. Hence, minus 3 by 5 is a local maximum and 1 by 3 is a local minimum. As another example, consider f of x equal to x plus 1 divided by square root of 5x square plus 35. This function is differentiable everywhere, and f dash of x is equal to square root of 5x square plus 35 into 1 minus x plus 1 into 1 by 2 times square root of 5x square plus 35 into 10x whole divided by 5x square plus 35, which is equal to 5x square plus 35 minus x plus 1 into 5x whole divided by 5x square plus 35 whole to the power 3 by 2, which is equal to 35 minus 5x whole divided by 5x square plus 35 to the power 3 by 2. Now, f dash of x is equal to 0 implies 35 minus 5x equal to 0, which gives x equal to 7. F double dash of x is equal to 5x square plus 35 to the power 3 by 2 into 0 minus 5 minus 35 minus 5x into 3 by 2 into 5x square plus 35 to the power 1 by 2 into 10x whole divided by 5x square plus 35 to the power 3, which is equal to minus 5 into 5x square plus 35 to the power 3 by 2 minus 5 into 7 minus x into 3 times 5x square plus 35 to the power 1 by 2 into 5x whole divided by 5x square plus 35 to the power 3. At x equal to 7, the second term in the numerator vanishes, so that f double dash of 7 is equal to minus 5 divided by 5 into 7 square plus 35 to the power 3 by 2 is less than 0. Hence, f has a local maximum at x equal to 7. Warning: as mentioned earlier, the second derivative test fails if the second derivative does not exist or its value is 0. For example, let f of x equal to x to the power 4, then f dash of x equal to 4x cube and f double dash of x equal to 12x square. F dash of x equal to 0 gives x equal to 0, further f double dash of 0 equal to 0, so that the second derivative test fails. However, it can be seen from the graph of f of x equal to x to the power 4 that x equal to 0 is a local minimum. Let us now look at a function involving trigonometric functions. F of x equal to minus cos 2x. Here f dash of x equal to 2 into sin 2x. Thus, f dash of x equal to 0 implies sin 2x equal to 0. By looking at the graph, we see that sin x equal to 0 at the points x equal to 0, plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, and so on. Thus, f dash of x equal to 0 implies 2x equal to 0, plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, and so on. So that x equal to n pi or x equal to n pi plus pi by 2, where n varies over all integers. Hence, there are infinitely many local extrema. We shall now classify them. For this, f double dash of x is equal to 4 times cos 2x. F double dash of n pi is equal to 4 times cos 2 n pi, which is equal to 4 times cos 0, which is equal to 4, which is greater than 0. F double dash of n pi plus pi by 2 is equal to 4 times cos 2 n pi plus pi by 2, which is equal to 4 cos pi, which is equal to minus 4, which is less than 0. Thus, x equal to n pi is a local minimum for each integer n, and x equal to n pi plus pi by 2 is a local maximum for each integer n. This is obvious as seen from the graph of f of x is equal to minus cos 2x. Look at another example, f of x equal to x square minus 1 to the power 2 by 3. We have f dash of x is equal to 2 by 3 times 1 by x square minus 1 to the power 1 by 3 into 2x for all x not equal to plus or minus 1, and f is not differentiable at x equal to plus or minus 1. F dash of x is equal to 0 implies x equal to 0. Hence, x equal to 0, minus 1, 1 are the critical points. F double dash of x is equal to 4 by 3 into x square minus 1 to the power 1 by 3 into 1 minus 1 by 3 times x square minus 1 to the power minus 2 by 3 into 2x square whole divided by x square minus 1 to the power 2 by 3, which is equal to 4 by 9 into 3 times x square minus 1 minus 2x square whole divided by x square minus 1 to the power 4 by 3, which is equal to 4 by 9 into x square minus 3 whole divided by x square minus 1 to the power 4 by 3. Thus, f double dash of 0 is equal to minus 4 by 3, which is less than 0. So, that x equal to 0 is a local maximum. We cannot draw any conclusion about the points x equal to plus or minus 1 as f is not even differentiable at these points. However, by analyzing the derivatives near these points, we may draw some conclusions. If x is less than minus 1, then f dash of x equal to 2 by 3 into 1 by x square minus 1 to the power 1 by 3 into 2x is less than 0, as numerator is negative and denominator is positive. Hence, f is decreasing in the interval minus infinity to minus 1. If minus 1 less than x less than 0, then f dash of x equal to 2 by 3 into 1 by x square minus 1 to the power 1 by 3 into 2x is greater than 0, as both numerator and denominator are negative. Hence, f is increasing in the interval minus 1 to 0. Thus, x equal to minus 1 is a relative minimum. By similar argument, it follows that f is decreasing in the interval 0 to 1 and f is increasing in the interval 1 to infinity, so that x equal to 1 is also a relative minimum. All these conclusions can be verified from the graph. Here x equal to 1 and x equal to minus 1 are local extrema, even though the function is not differentiable at these points. Such points are called cusps. Now, let us summarize. In this session, we have discussed local maxima and local minima of functions and the method of identifying them by using first and second derivatives. We have seen that by evaluating the function value at local extrema and at n points, we can find the absolute maximum and minimum value of functions. In the next session, we will continue the study on extreme values of functions by extending the domain of functions to unbounded intervals. We will see that even if the domain is not a finite closed interval, the absolute extreme can be evaluated provided it exists. Hope you enjoy the session. We will meet again shortly. Have a